Hey everyone, welcome to the first section of Chapter 2, Exam 2 Notes, Section 2.6. And so at the beginning here, I want to kind of pose a problem to you, one similar to how we started the last unit. So how can we find the equation of the tangent line of the given equation x squared minus 7x plus 2 at the point of 2 comma negative 8? Now I've already graphed it for us. And so if we kind of thought about this like x squared at the point 1, 1 like we did in the last unit, we kind of had to like pick points on the graph or the actual parabola, find those secant lines and kind of work our way back, right? And so here I kind of want to do the same thing, but we know that that's not really super duper efficient, right? So I want to kind of give a guess to kind of have a starting point anyway, kind of see how close we get. And so for the point 2 comma negative 8, I'm going to pick the points 0 comma negative 4 and 3 comma negative 11 and see what I get. So just using slope intercept or the slope formula that we kind of talked about and kind of go from there. So it doesn't matter which ones you have, first or second, just as long as it's the same order. So I put the negative 11 and 3 first, so it looks like I get negative 7/3, okay? But we'll come back to it. So looking here, I want to be able to give you a formula or kind of a process to help us find our tangent line or that slope there a little bit more efficiently. So here you go. It's called the derivative. So the derivative of a function of f at a number a, denoted as f of or f prime of a. So that's what that apostrophe means. We can write this in one of two ways. Using f of x minus f of a divided by x minus a as x approaches a, or I can say the limit of f of a plus h minus f of a divided by h as h approaches 0. Those are two different ways of doing the same thing, and I'm going to show you how they look, and they're going to get us the same answer. So the tangent line at a function at that point is going to actually be the slope, so the derivative, they're the same. We call that instantaneous rate of change for the function of x with respect to x as x approaches a. We can also talk about the position function with respect to time. So instantaneous velocity is our derivative, or f prime of a at a. Speed is going to be the absolute value of velocity there. Okay? So let's go ahead and go back. We're going to try these. We're going to do both. We should be able to get the same answer. Now when I do this, I want to first find, kind of plug in what I know. F of x is the function. Remember, a is going to actually be the x value that I'm looking at, or the point on the graph that is the x. So I'm going to be approaching 2. Just looking at that, I should be approaching negative 8, right? But I'm not going to actually use that. That's not going to be my answer here. So I'm going to plug this thing in. So f of x is going to be the function that I start with. Plugging in 2 into the actual function gets me 2 squared minus 7 times 2 plus 2. And so simplifying that gets me kind of the following expression. I'm able to kind of figure out what the second parenthesis is. I should get negative 8, which is what 2 is. If you knew that at the beginning, you could just plug it in right from the get-go because it is f of 2. So sometimes you will know what f of a is for these, and you can plug them right in. Sometimes you won't, so then you just kind of have to plug it in as you go. So then I get the following expression of x squared minus 7x plus 10. I can't really plug in 2 yet because of x minus 2 in the denominator. It would be undefined, so I got to factor. So I factor it to be x minus 5 times x minus 2. Then I see that x minus 2's cancel each other out, and now I can deal with the expression of x minus 5, so plug in the 2, I get negative 3. Now before I find the tangent line's equation, because I have the slope, I want to show you that the other one works as well, because after that finding the equation is the same process for both of them. So I'll just do that once for us. So here, notice that we have an a. That is the same a that we used in the previous example right there. So it's going to be 2. So I already know what f of a is, or f of 2 is. It's negative 8. So if I want to, I can just plug that in. Now, a lot of you are probably going to get thrown off by the 2 plus h here. Remember, that is our value, or our x, so I'm going to plug it in for where I see x. So I get, instead of x squared, I get 2 plus h squared. Instead of negative 7x, I get negative 7 times 2 plus h. Like I said, I already know what f of a is, so I plug in negative 8. Our denominator is just going to be h, which makes it a little simpler at the end, which is kind of nice. But I'm going to multiply 2 plus h squared out. Remember, that's 2 plus h times 2 plus h. That gives me 4 plus 4h plus h squared. You can switch that around if you want. Now, I got a lot of like terms to kind of simplify here, so I'm going to put them together. Nothing goes with h squared, so that's fine. 4h and 7h go together, so it gives me negative 3h. 4 minus 14 plus 2 plus 8 actually cancels out and leaves you with 0. So I can write minus 0 or plus 0, but I really don't have to. So I can just leave it as h squared minus 3h divided by h. Simplify, so h squared becomes h, minus 3h becomes minus 3, and now I can plug in 0. And so 0 minus 3 gets me negative 3. Notice that I got the same slope. So now that I have the slope for my tangent line, I'm going to use something that we've talked about in Algebra 1 and 2 before to help us find the slope, or the equation given a slope and a point. So I plug in my slope of negative 3. I'm going to plug in the point of 2, negative 8, and actually simplify and solve. You do not have to use slope-intercept form if you don't want to. You can use any other equation for a line if you wish. But that allows me to find the y-intercept of negative 2. Sorry for my poor line there, but I get y equals negative 3x minus 2. And that would be my answer there. So now, kind of tying into kind of ideas that we've talked about already. So average rate of change, or arc. Remember, that's just the slope of the secant lines. We've done that before. We did that in the last unit. Nothing new about that. So now we're really going to focus more on the instantaneous rate of change for our functions, or the IRC, at a value of a, so which is the slope of the tangent line. So given a point on that kind of graph that I know, which is on the graph, I'm going to take the limit of the secant lines using the equation that I have and the actual point that I know. Now, just so you know how those two kind of formulas tie in together, if I think of x and rewrite that so that x minus a can actually be set equal to h, I can rearrange that to say x equals a plus h, and so that's kind of how I get the second one. It's actually an easier form of it, so we're going to use that one more often. Just to reiterate, s of t is going to be the position function with respect to time. Arc is your average velocity, and then IRC is going to be your instantaneous velocity there. Okay. So now let's actually apply this to a problem that you're going to see during your homework. So I have an object that's dropped 1,000 meters from up above. Then the velocity of its position with respect to time is set up with that formula. I'm just plugging in the values at position 1, 2, and 3 for time, for seconds, for letter A. So at 1, it's going to be 995.1. At 2, it's 980.4. And at 3, it's 955.9. Okay. The next letter just wants us to be able to find the average velocity, so the arc for these values. Notice that they didn't give us what 0 is, but if I plug in 0 for my function, it's 1,000. So I'm just going to plug that in. So 1,000 minus 995.1 divided by 0 minus 1. That'll get me 4.9 on the top divided by negative 1 on the bottom. So it's negative 4.9 meters per second for that average velocity there. I'll do it for the second 2 points that I have. So 980.4 minus 955.9 divided by 2 minus 3. That's going to get me 24.5 on the top divided by negative 1. So negative 24.5 meters per second. Now, for both of those, it makes sense that we have a negative velocity because we're going down. We have a negative slope for those, so that kind of tracks. So letter C wants to know when is our object going to hit the ground. Now try to keep in mind that I'm not asking about when it's resting on the ground. So I'm asking for when it first initially hits the ground, that first impact point, because remember our function doesn't know about like gravity and ricocheting or any of those things right now. So you kind of have to keep those things in mind. So when it hits the ground, your height is 0. So I'm going to set my equation equals 0. So it allows me to solve both sides. So moving the 4.9 t squared to the left, divide by 4.9, and then I'm going to take the square root. And so then that will get me the time value of 14.29 seconds. It's actually not a round decimal, but try to keep your number as exact as possible in the calculator because you'll need it for the next part. Okay? But we can also write this as an ordered pair, right? So at time 14.29 seconds, our height is 0. So I can write that as an ordered pair. Right, now letter C wants us to actually find the velocity at the point of impact or when it hits the ground, right? So I'm going to use the second one to kind of help me out, the second kind of formula. So f of t plus h minus f of t, or we can use a. It doesn't matter which one we kind of look at. Now remember, a is the point that we just found, so that's 14.29. Because that's the point of impact, right? That's the amount of time it takes to get there and to touch 0. Now, because I'm plugging that in, I already know what f of 14.29 is because I just found it, right? So I can plug that in and make it 0. But I do need to plug in 14.29 plus h into t to help me find the rest. So I can not worry about the minus 0. I'm going to have to multiply that 14.29 plus h out because it's 14.29 plus h times 14.29 plus h. So multiplying that out gets me actually to 24 because it's 14.29 squared. So I already have that number, 204.08. Times 2 gets me 28.57 h, and then plus h squared. And then I'm going to have to distribute that negative 4.9 through to everything. And so I get 1,000 minus, actually, negative 4.9 times 204.08 is actually 1,000. Okay, and then negative 4.9 times 28.57, which is actually going to be a nice number as well, so it's negative 140h. And then negative 4.9 times h squared is just negative 4.989h squared. The thousands cancel out. I'm left with negative 140h minus 4.9h squared. I can reduce all those, taking out an h. So leaves me with negative 140 minus 4.9h squared. Sorry that I forgot the square there. And then putting in 0 there just leaves me with negative 140 meters squared. So that's the actual velocity at impact there. So kind of looking back at E, it wants me to evaluate the same thing that I just did, except instead of putting in 14.29, they want us to use A instead. So I'm going to do the exact same steps that I did before. I'm going to plug in 1,000.49 times A plus h squared. And then same thing as 1,000 minus 4.9 A squared. Because now I don't really know what A is, so I can't just say it's 0. And then I want to simplify. So on the inside, it's A squared plus 2AH plus h squared. And then I can just distribute the negative through there. For the next part, distribute the negative 4.9 through to get the following expression. I also can get those thousands to cancel out to make my expression a little easier since there's no parentheses holding me back. And then I see that I have 4.9a squared. I kind of forgot that negative on the front in the last one, so cancel those out. And then I am left with two terms on the top that both have h, so I can reduce those. And that allows me to plug in 0 for h, which, just like in the last example, that takes care of that last term. So really, at any point in my kind of process, negative 9.8 times a is going to be the velocity as I'm dropping that object from 1,000 meters up based on what I know. Okay. Example 2 wants us to be able to find the limit of the derivative of some function f at some number a. They just want us to state the function of f and a for each of the examples. So here, I want to look at these, kind of first determine which formula they're talking about. So for letter A, it is h approaching 0. So that bottom should give away that you're talking about the second formula. And so here, 1 is actually our A. And because it's on the inside, because it's a plus h, that is actually what kind of dealing with our function. So because that's on the inside, it's taking it to the 10th power. So I'd say x squared, or x to the 10th. To confirm this, I can plug in 1 or what our a value is and see if I get that last term, because that's supposed to be our f of a. And so it looks like I do. 1 to the 10th is 1, so that's actually my answer. The second one is actually a lot easier to kind of see, because x is approaching a value and it's x minus a in the denominator. So both of those are 5, so that's got to be my a. And then in the top part, f of x is actually the first term in that binomial. So it actually tells me what my f of x is, which is 2 to the x. Just like the last one, I can confirm if that's true. So if I'm saying a is 5, I can plug it in. So 2 to the 5th is actually 32. So that's true. Okay, so that's all they're really wanting for those, is just for you to identify the function and what the a is in those cases. Okay, now here, the last one, I want to be able to sketch a graph of the function given the information that I have. Now, there's I can't write every possible answer to these, so I'm going to give you one. Just as long as you're using the information that you're given that is required, that is all that's needed. After that, there's more flexibility to see what these graphs are. So the first thing they give you is a points of 0, 0. So I graph that. The rest, because they're all f primes, they're telling you the slopes. So at f of 0 or f prime of 0, your slope is 3. So I can kind of draw in what I think that slope of 3 is. So I can kind of make a sketch of what I think it needs to be. At f of 1, it needs to be 0. Now, I could put it up there at 3, or I can kind of move it down. Notice that they don't tell you what your actual value needs to be, so I can kind of put it anywhere. So I'm actually going to put it at 2, because it'll be a little easier for me to get from a slope of 3 to a slope of 0. So f prime of 1 is 0. So notice they're telling you your x value, and at that point, that's what your slope should be. So f prime of 2 is 1, so I need to also be able to start going back up from that point. So if I draw in what I know right now, I can also draw what I think the slope is approximately, and I can try to match that to whatever I'm doing. So that's about a slope of 1, or what I think of 1, and so I can match that. Now, that is not the only answer. You can kind of start the other side, going down and coming back up, and then doing the same thing. There's lots of different kind of possibilities, just kind of like what I was doing there. So I can kind of go at 3, but then taper off a little earlier. I can do that, go down at 0, and go back up. So it kind of just depends. Okay? Hopefully that's helpful. Thanks. Have a good day.